Hi everyone, today we're going to keep talking about neural networks. So in particular, we're going to talk about multiple, two-layer neural networks, multiple output, one output, vectorized form. We're going to talk about how to feed neural networks, and in a second video later on, we're going to talk about neural networks for tabular data. So this is the picture we have been kind of working with. And in the pictures, we have two input variables, the exam and the grades. And as we have talked about before, those two input variables are going to go and we're going to have a linear combination of those variables go into, say, the judge one is going to have a linear combination of those, and then after that we're going to do some kind of score after that. For example, in this case, we have that the judge one is computing minus 1 exam plus -8 grades plus 40. That's basically the function that judge one is computing, and then it's gonna put a sigmoid on top of that to get a score. Okay, so the function that judge one is computing is a linear function of the input variables and then a nonlinear function. In the same way, the judge 2 is computing a linear combination of the input functions and then a sigmoid on top. Okay, so, and the president is computing a linear combination of the score of judge 1 and the score of judge 2, and then putting a sigmoid on top. And here are the values that we have for this particular network. And what we're trying to do here is to have a function that, given an exam and grades, we're going to decide if a student gets accepted to the university or not. So what we have here is that we can write this network, this particular network, in matrix form. So here we have W1 is basically are basically all of these weights that are in the first layer. B1 are the biases that we see kind of here and here. Then W2 are the weights we see in this second layer, and B2 is the bias that we see here. So here are the parameters of this particular network. So how many parameters do we have here? So in the first layer, we have W1, which is a matrix which have 4 numbers, and then B1, that is the bias, that have 2 numbers. And then W2 has 2 numbers, and the bias has 1 number. So in total, we have 9 numbers. So those are the number of parameters we have in this small network here. So now, if you remember, so how we actually computed, so what was kind of the formula that we did to compute this model. So first we take x, which is a 2-dimensional vector, we multiply by the matrix W1, we sum the bias, and then we put sigmoid on that. Okay, and that will give us something that we call A1. So then we take A1, multiply by a matrix, in this case it's a vector, sum a bias, and take the sigmoid of that, and that is called A2. And that's also our prediction as well. So now that we know how to do this, so can we compute the final score that we will give to a student that have 5 in the exam and the grades are going to be 5 as well? Should we give to students, should we accept the students into the university? That's kind of the question, right? So first of all, let's compute what we in a previous lecture called Z1, which is basically what happens after we do the linear transformation. So we're going to have this matrix. Going to multiply by 5, 5, and we're going to sum 40. Okay, so this is equal to minus 5 minus 40 plus 40 is a vector. So, and here is minus 35 minus 10 plus 40, and this is equal to minus 5 and minus 5. So that will be Z1, right? So how do we get A1? So A1 is going to be equal to sigma of minus 5 and minus 5. The way we actually compute this is element-wise. So this is going to be actually sigmoid of minus 5 and sigmoid of minus 5. And if we check, with our calculator, that is going to be something like, I have it here, is going to be something like 0.006. 0.006. Okay, so after that, what we do is that we want to compute Z2. So how we compute Z2? So we take W2, which is minus 2 minus 3, and take basically a dot product with 0.006, 0.006, and then plus 0.1, which is the bias, and this will give me 0.0665. Now, to get the final prediction, the final score, we take, y hat is equal to A2 which is equal to sigmoid of this Z2, which is this number here, 0.0665. And this number will give me something like 0.5166. So do we accept the student or not? Well, it depends on what is the threshold that you are using to get a hard prediction. If the threshold is 0.5, this is definitely bigger than 0.5, and we will accept the student. If the threshold is something more like 0.7, then you would not accept the student. Okay, so I hope this clarifies how we compute a neural network in this kind of vectorized way. So let's talk about, in general, how many parameters do we get in a two-layer neural networks. So first of all, let's think about, so how big is the input? So we have some of these inputs. So we have, say, x, and x is x1, x2, xd. We can draw a little picture here and say we have d neurons. This is our input layer. And then we want to transform that into m layers. So this would be our hidden layer, would be m layers. And finally, after that, we want to transform that into k classes. Okay, so if you look at, say, one of these elements here, so how do we compute the value of this element here? So let's say that this is, zj, right? And then after that, zj1, and after zj1, we compute aj1. So note that z1 is a vector that has dimension m, and it's going to be z1, z 2, 1, Z, M, 1. So the script on the top here has to do with layer, and the subscript in the bottom here has to do with the dimension. Okay, so if you think about this, how to compute one of these neurons here, see how to compute ZJ or AJ, right? 1. We have to basically do a linear transformation of the inputs, so we're going to need D weights plus a bias. So we're going to need, for each one of them, we're going to need D plus 1 numbers. And since we have M of them, so the first layer is going to need M times D plus 1 elements. In a similar way, if you think about computing here is like Z to, say, K, you know. So to compute Z to K, we're basically going to take as an input this hidden layer that has M elements. So we're going to have to have M weights plus a bias. So we're going to need M plus 1 plus a bias, but we have K of those, so we're going to have to compute this times K times. So the sum of these two, M D plus 1 plus K times M plus 1, that is the number of parameters we have in this case. So far we have been talking about 2-layer neural networks, and this one is a 3-layer neural network. So how we count the layers? So the way to think about the layers is that, so here you have some parameters to go from x1, x2, from x to the first hidden layer. That counts as 1 layer. Then here you're going to have some other set of parameters to go from the first hidden layer to the second hidden layer. That counts as a second layer. And here you're going to have some other set of parameters to go from the final hidden layer to the output layer. And these are the third set of parameters. So that's how you count the number of layers. So if we think about the equations for these networks, right? So far we basically talk about how to compute Z1, and then how from there to compute A1, right? And then how to compute Z2, and from them how to compute A2. But there is nothing that tells us how we cannot keep going. Actually, there is a typo here, and this should be a 2. So we could keep computing these different things. So in this case, since we have a 3-layer neural network, then we're gonna keep going one more time. We're gonna stop at C3, and since the output layer has just 1 neuron, we know that it's either a regression problem, in which case y hat is gonna be Z3, or a binary classification problem in the case in which y hat is gonna be the sigmoid of Z3. And in all of these cases, H is a nonlinear activation function, which is applied element-wise. So let's talk about the PyTorch models, right? Like we have already seen that if we have a network like the first one here, this is our PyTorch model here. So how do we write a PyTorch model for the second network here? So let's think about that for a second. So what we do is to just kind of write another layer, basically. So it would be something like this. So you do model equal to sequential. I'm gonna omit some of the NN, torch.nn sequential, and then we do NN dot linear And there are two input features, so I'm going to have a 2, and the first layer has 2 neurons, so we're going to have a 2 here. And then we have sigmoid, or you can use any other activation function you want. And then we have nn.linear, and this is also going to go from 2 inputs to 2 outputs. So it's going to be a 2, 2. Then we are going to have a sigmoid again. And finally, we're going to go from these 2 inputs to 1 output. So it's going to be another linear layer. So this is the model that we will get. So in this case, what we are changing here is that we are going from a model that outputs just 1 neuron to a model that outputs 3 neurons. So we have 3 classes. So what is the difference between the model we have up here and how would we write a model for the second example? And here is very simple. So what we're going to do is basically just change that for a 3. Okay. We also would have to think about the last activation function if we're going to do classification, but we're going to talk about that later. So in this case, what we're changing is that the number of input features used to be 2, but now we want to have 3 features instead. And here what we're changing is basically just kind of the input features here, just putting a 3 there. So for a second, let's talk about activation functions. So the activation functions is the non-linear function that are used after the linear transformations. And there are 2 types of activation functions. One are the ones we use in non-final layers. And in that case, many different functions will work. And the ones that we use in the last layer. And this is usually defined by the problem they're trying to solve. So let's see how we do that. So first, let's talk about the non-final layers. In this case, we can talk about different functions. People used to use a sigmoid, but they don't use it anymore. Basically, because when you want to train deeper networks, sigmoid is not very good at getting the model to train very well. So tanh, which is similar to sigmoid, was also used, and now it's used in recurrent neural networks, but not that much in feed-forward neural networks. And what people tend to use these days is more a function called ReLU, or some kind of ReLU-like function. And ReLU is a very simple function. So if you see here, we have it's a function that is going to be 0 for anything that is less or equal to 0, and then it's going to be the function basically z equals z for all the other part. So it's going to be it's a piecewise linear function. So here are some other examples. So there is a function called leaky ReLU, which is very similar to ReLU, but so basically the function is 0.1x for x less or equal to 0, and x for x bigger than 0. There are some other, so there is one called ELU, which is similar to leaky ReLU, but it's using a different function for x less than 0, and so on. So all of these activation functions can be used for intermediate layers. And then we have the final activation functions. This is the activation functions that you use at the end. So, and pretty much what happens is that when you're talking about binary classification, we're going to use sigmoid, because what we're taking is one number. That number, Z2, for example, could be between minus infinity to plus infinity, and we want to turn that number into a probability. So a way to do that is by doing a sigmoid on top of that. In the case that we are talking about regression, what we use is the identity function. So basically, we don't do anything, we don't use any activation function. And in the case that you have a multi-class classification, we're going to have, say, k numbers, right? And we want to turn these k numbers into k probabilities that sum to 1. So we're going to use a softmax function. Yeah, so let's actually look at a very simple two-layer neural networks that has 3 outputs. So, and basically what we're going to do is pretty much the same thing we did before. We're going to transform x into z1. To get a1, we do ReLU, for example, of this z1. And then we do a linear transformation of this a1, okay? And then after that, what we're going to do is softmax. So let's remind ourselves how softmax is computed. So the way we do softmax is that we exponentiate all of the elements of z2 and then divide by the sum of all of these exponentials to get a probability. So with the exponential, what we do is to take numbers that could be between minus infinities and plus infinity, and we turn them into positive numbers. And then we divide by the sum of all of them just to get a probability to be summed into 1. So let's do a little bit of practice here. And if you have issues and don't understand softmax very well, maybe it's a good time to stop the video and try to do it on your own. But I'm going to try to do the computation as well. So let's compute this and then also compute the loss of this. So we're going to compute y hat, so all the probabilities, and then we're going to take this is our y, or this one here, and we're going to compute the loss. Okay, so basically, so y hat is a vector of dimension 3, right? So y hat is going to be y hat 1, y hat 2, y hat 3. And in the case 1, okay, in both cases, because the z2 is the same, we're going to get the same probability. So we're going to get y hat 1 is going to be e to the 0.1 divided by e to the 0.1 plus e to the 10 plus e to the 100. Okay, so similarly y2, the second element of the prediction is going to be, second probability is going to be e to the 10 divided by e to 0.1 plus e to the 10 plus e to the 100, right? And then we have y3 hat, and this is going to be e to the 100 divided by e to the 0.1 plus e to the 10 plus e to the 100. Okay, so those are the probabilities that we're going to get. And then in the case 1, to compute the loss, what we do is that we're going to have minus log, and we have talked about this before, of what? Of z2, sorry, not z2, is minus log of y2 hat. Why is that? Because that's the one we have in here, right? So if you remember, the loss would be something like this. K equal 1 to k of minus log, sorry, it's going to be yk log of yk hat. Okay, and since the only yk that is 1 is the second one, then that's what we get. We get the log minus the log of y2 hat. Okay, so and that would be minus log of e to the 10 divided by e to the 0.1 plus e to the 10 plus e to the 100. Okay, and this is equal here to what? This is equal to the log to e to the 10 to the 0.1 minus 10 plus e to the 10 divided by e to the 10, which is going to give me 1, plus e to the 100 minus 10, which is going to be e to the 90. Now, this is going to be a very small number, and this is 1. So this is approximately just the log of e to the 90, which is going to be 90. Okay, so that's the case 1. Yeah, so that's the case 1. And let's look at case 2. So in the case 2, what we get is minus log of y3 hat, which is what? Which is minus log of e to the 100 divided by e to the 0.1 plus e to the 10 plus e to the 100, which is equal to the log of, just basically take this minus 1 and turn the fraction the other way around, right? So undo e to the 0.1 minus 100 plus e to the 10 minus 100 plus 1. And these numbers here are very, very small, almost like 0. And so this is approximately log of 1, which is going to be equal to 0. Okay, so basically, in a way, it's clear that since we have 100 here, the exponential is going to give, and all the other numbers are kind of far away from 100, the exponential is going to give all the probability to this like 100 here, and it's going to give a loss of 0. So the probability is everything inside here is going to be almost 1, and then the log is going to be 0. So let's remind ourselves on how do we do hard predictions for classification. Remember, we talked about this a little bit before, but I wanted to remind you of that. So if we have a two-layer neural network, we get y hat equal to sigmoid of z2. Okay, how do we get a hard prediction? That would be a soft prediction. It's a probability, right? A hard prediction would be basically by saying, hey, we have a threshold, and say even if the number is bigger than the threshold, the probability, then we're going to be a 1, and otherwise it's going to be a 0, right? So the threshold tend to be 0.5 sometimes. And I just wanted for you to know that, so basically if this is bigger than threshold, is, is 1, and it's going to be 0 otherwise, right? I just wanted you to see that y hat bigger than 0.5 is equivalent to z2 bigger than 0. And I want you to understand that, because I use a lot that in PyTorch. So instead of computing the actual probability, if I want to do a hard prediction, I will just use z2. Okay, so why is that? So if you guys see here, this is the function, the sigmoid function. So suppose I have my function z or z2 here. So if z or z2 is bigger than 0, sigmoid is gonna take that number and make it bigger than 0.5, because at 0 we have 0.5. If it is bigger than 0, I'm gonna be somewhere over here. It's gonna be bigger than 0.5, right? And the other way around, if z is less than 0, I'm gonna get a probability that it is less than 0.5. Okay, so it's equivalent to, if we're gonna do a hard prediction, to say that, you know, if z2 is bigger than 0, than if y hat is bigger than 0.5. Now let's talk about the case of the multi-class classification. So the soft prediction here is a softmax, which is going to give you some probabilities. But again, when I am talking about hard prediction in PyTorch, for example, I am going to take, the hard prediction is the argument of the maximum probability. So you're going to take the class that have the highest probability to be your hard prediction, right? So for example, if you have like, you know, y hat is equal to 0.1, 0.5, 0.4, the class of the second element is going to be your higher class. So if this is class 0, class 1, class 2, then the class 1 is going to win, right? So basically that's how we do hard predictions. So it is equivalent that instead of doing the argmax of these probabilities, of the softmax, you can do the argmax of Z2. Because if you have, then, so these numbers came from a softmax function, right, of Z2. So when you have those numbers Z2, the higher number is going to give you the highest probability. So you don't have to convert to softmax to understand which one is going to give you the highest probability. The highest number is going to give you the highest probability. So you can just take the argmax of Z2. Okay, cool. Okay, so how do we fit a two-layer neural network? So here, this is very, it's kind of similar to what we have done before. So we know that we have these parameters, W1, B1, W2, B2. And in a similar way as before, we can define some loss function. This is the loss function for regression. This is the loss function for binary classification. This is the loss function for multi-class classification. And what we're going to do is that we're going to initialize all those parameters with some random numbers, and we're going to use gradient descent, or a version of gradient descent, to fit our model, right? So we're going to do an iterative process to fit the model. So what we're going to do right now is that I'm going to go through the process of derivating the gradient descent equations for a two-layer neural network in the case of regression. So in this case here. And then I'll leave you the binary classification for homework. It's a bit more complicated, but it's a good exercise. Okay, so let's do that. So what we have here is that so we have our error function, which I'm going to call E, and this function E is 1 over n sum small n equal 1 to capital N y n minus y hat n squared. You're going to be annoyed that I used to use I and now I'm using small n, but it's because I'm using it for something else, so I don't want you to get confused. So basically, and usually when we are taking, so we're going to have to take derivative of all of these type of weights that we have. So we have this matrix W1, which have weights W, J, I, 1, right? And then we have B1, which have weights B, J, 1, right? And this is I from 1 to D, if we have a dimensional vector, and J from 1 to M, okay? And then we have W2, which have, we have, so these are capital W's, right? So, and the elements, we're going to call small case WJ2, okay? And then we have B2, which is just one number, okay? So we're going to have to take derivative with respect to all these numbers, okay? So let's think about this. So say we're going to take a derivative with respect to some kind of W, any W, right? So we know that we can basically easily just basically say, well, there is a minus here, there's a 2, there is yn minus y hat n, and then there is d y hat n dw, okay? So for simplicity, I am going to start by taking all of this derivative with respect to all of these different weights that we have, right? And also, for now, I am also going to drop the n to make the derivations kind of simpler, and then I'm going to come back and plug it into this equation later, okay? So the first thing we have to think about is, so let's think about the equations we have, and we're going to have to take the matrix form that we have so far and kind of write it in a more friendly way so that we can take derivative in an easier way, okay? So we have x is a d-dimensional vector, so x is x1, x2, xd. So, and we have z1, which is an m-dimensional vector, right? So which is z11, z21, and zm1, and this is an m-dimensional vector. And let's think about, so if you remember, like, the equation is like this: z1 is equal to w1 times x plus b1. Okay, so we have, the way to kind of draw it is that we have a matrix w1, right? And we're going to multiply that by a vector x, and we're going to sum b, okay? So to get one of these elements, okay, and this is going to be a kind of an m-dimensional vector right here, right? To sum all of the elements, to basically, to get one of these elements here that I'm going to call z1j, to get that element here, what we do is that we take this row, the jth row of this equation, and we multiply that by x, kind of a dot product, right? And then we sum this element here, and we get that, right? So this is just basic matrix multiplication. So to write that, we just basically are going to sum over the dimensions of x, so over I, okay, equal 1 to d. This is the dimension, this is x, is d-dimensional, it has d features, right? And we're going to sum wji times xi, okay? And then we have a bias, which is b, so this has like a 1 here and a 1 here, and that's our equation here, okay? Then we're going to have a1j, and this is simply h of, where h is just a nonlinear activation function of cj1, okay? So what else? Then basically we have a simpler second layer, because a second layer give us just kind of one number. So basically what we have is that Z2, which is just a one number in this case, is equal to the sum over J of Wj2 times Aj1 plus B2. Okay? So those are the equations that we have. And you know, by the way, because we're in regression, this is going to be our y hat, right? So basically, what do we have to figure out? So we have to figure out the derivatives with respect to, you know, these guys and these guys and these guys here and these guys here, basically. So we have to figure out the derivative with respect to all of them. The simplest one seems to be this one here, right? So we have to figure out the y hat dB2. But that's quite simple, because if you look at this equation here, you realize that this is equal to 1. Agree with me? Okay, that one was easy. So what about, let's talk about dy hat dwj2. I don't know if you guys agree with me that this is just aj1. It's just that this is a kind of a linear function with respect to wj. So you just get what multiplies a linear function. Okay, so those are the simpler ones. So let's talk about the ones that are a bit more complicated. So the next one I have is dy hat dB1j. Okay, so this is equal to the sum over j prime. I'm going to put j prime to differentiate this particular j with summing over some j's, right? So I'm going to sum over some j's. So I'm going to call the sum over j prime, right? To differentiate if what the particular j I am differentiating with respect to here, right? So, and what we get here is that this wj prime into doesn't depend on bj at all, right? So what depends on bj is the aj itself. So we have this daj1 dbj, and there is a prime here. Okay, and then b2, this part here, doesn't depend on bj1 either, so that we can take it off. Now let's look at this for a second. So let me see if you guys agree with me. So they j prime on 1 dbj. Okay, so I claim, and this is equal to 0 if j is different than j prime. And basically, it's just that these weights, W, J, I, they're all different for different J's, right? So you're multiplying for weights that are different for different J's. So unless, so the definition of, AJ is H of ZJ, right? And CJ, just the ones that have the same J are using this WJI, right? So if you have a different J prime, it's just going to be 0 because it doesn't depend on BJ. Okay, so, and otherwise what we have is that this is going to be H prime of ZJ1 DCJ1 DBJ1. So what is dCJ1 dBJ1? That is basically just 1, because this is the equation here. Okay, so basically this thing here is just 1. Okay, so let me kind of write down what I have here, because I have a mess. So let me write it down. So what I got is the following: dy hat dBJ1 is equal, so we don't have to do the sum, right, because it's just one of them, is equal to Wj2 times H prime Cj1. Cool? I hope it is. So, okay, cool. So finally, what we have to do right now is the most difficult one, which is dy hat dWji1. Okay. So, and here we have the same thing. So we have this equation here for y hat, right? So what we have is this like summing over some j prime of Wj prime 2, and then we are gonna do like dAj1 dWji, and there is a prime here. Okay, and we're gonna see the same. We're gonna see that this is actually equal to Wj2 times dAj1 dWji, and that's for the same reason, basically. So all of the other j primes that are not equal to j, you can just have derivatives that are 0, right? So let's just try to figure out this derivative right here. Okay, so if you remember aj1, okay, yeah, aj1 is equal to h of zj1, right? And this is equal to, so if you do the derivative of this with respect to the wji, you're gonna get h prime dzj1 dwji, right? So what is this derivative here? Okay, so let's actually go back and look at the equation. So okay, actually let me write it down. So what is the equation of zj1? Okay, so this is the sum over I equal 1 to d of wji xi plus b, okay, there is a 1 here, and plus bj1. Okay, so what is the derivative here? So the derivative is gonna be xi. Okay, so what we get here is h prime zj1 times x I. So finally what we get is dy hat dwji1 is equal to wj2 times h prime of zj1 times xi. Okay, so right now it's just time to put all this together, right? So if we go back and look at what we had before, so for example, I'm just going to write one of them because the other ones are going to be very similar. So if we have, you know, DE dWji1, okay, it's going to be minus 2 over n, the sum over small n equal 1 to large N of yi minus y hat n, sorry, n here, you know, and then we're gonna have, we're just gonna plug this in, right? So we're gonna have wj2, and this is the complicated part. this wj2 is gonna be on n, evaluated on the point n, right? So here this is a square, and then the other one is gonna be n. I definitely avoid writing this in general. So times h prime on zj1 in n, okay? And that's gonna be xin, which is the ith dimension of xn, which is the, so xn is the nth observation, right? And xin is the nth feature, the ith feature of the observation n, okay? Okay guys, so I hope this is good, and then basically remember like wij1 is just gonna be going to wji1 minus dwji1 multiplied by some learning rate. Okay, thank you for listening.